Okay, now that we've looked at a four-stroke petrol engine, we're going to have a quick look at some efficiency formulas. Now, again, there's a few of these that you need to know, and you've got to be really kind of comfortable in the difference between the different efficiencies that you might be asked to work out. So there's probably 4 or 5 different bits of terminology you need to know, and you need to be really kind of comfortable in which one you're being asked for. Again, let me just here and get my laser pointer up. Okay, so first of all, we're going to look at input energy. Okay, the engine is used or uses fuel to do some work. So when we are looking at input energy, this comes from the fuel itself. Right? If we look at the energy density of a fuel, so how much energy is stored within a certain amount of fuel, we call it its calorific value. So a bit like food calorific, the energy in a certain amount of stuff. So calorific value. All right, and it's energy released per unit mass of fuel when it's burnt. Now, if we look at input power to an engine, what we end up with is my input power is the calorific value of the fuel. Okay, so the amount of energy in a certain amount of fuel multiplied by the flow rate of that fuel. So how much of that fuel is going into the engine per second. All right. I want you to pay careful attention to the units here. So if we are looking for power, which we know is going to end up in a unit of watts, and 1 watt being joules per second, we've got calorific value of fuel, okay, and energy density of this fuel is 40 megajoules per kilogram. So our unit is joules per kilogram, essentially. So that's our calorific value. And as the car uses fuel at a rate of however many kilograms per second, that's my flow rate. All right. Now, when I multiply these together, I'm going to multiply joules per kilogram by kilograms per second. So those kilograms are going to cancel each other out, and I'm going to end up with joules per second, which is going to give me my power rating in watts. All right. You need to be careful. You will normally get the calorific value of fuel in joules per kilogram. That's fairly standard. Sometimes they try and trip you up by giving you the flow rate per minute. So it will be kilogram per minute instead of kilograms per second. And you've got to make sure that you're always doing it in kilograms per second. So let's look at this question. We've got a 40 times my value down here. We're just plugging those numbers in. So 40 times 10 to the 6, remember it's megajoules, so 40 times 10 to the 6, times my flow rate in seconds gives me my 60 kilowatts of power coming in. All right, so that's input power. Now let's have a look at the work done by my engine. We looked at these PV diagrams. We've spoken extensively about the area under the graph being the amount of work. And we've talked about these closed loops and the idea that if we want to work out the amount of work the engine is doing, we need to work out the area of that loop. All right, so area of my indicator loop. Now, at A level, it might be as simple as counting the squares within it. So if you work out the value, so you multiply 1 square of pressure by 1 square of volume, whatever your scales are on these two axes. If you work out the value per square and then you count the number of squares and multiply your value per square by the number of squares, then you'll end up with your kind of work value in here. All right. If we look at why the change in internal energy is 0 in 1 cycle, so let's have a look. We move from this point, we heat it up, we pressurize it, it expands and comes back down. Well, what's happening there is it's returning to my start pressure, volume and temperature. I end up back at this point over here. Okay, so my change in internal energy must be 0. Then we kind of go on to this part here. If we know my change in internal energy is 0, it means that my first law of thermodynamics is my heat energy is equal to the work energy that comes out of my my engine. Okay. Now, what we can work out from this, and if you think back to that energy diagram that we had, if you go back to the kind of flow diagrams, okay, my heat engine diagrams, I had QH going into a system, and that was equal to the work that the engine does plus the amount of energy that goes into my cold temperature sink. All right, so if I rearrange that formula, the amount of work the engine does is the amount of heat energy that gets put in minus the amount of heat energy that gets booted into that sink. Okay, so we can work out the amount of work that's being done in terms of temperature. So QH, the amount of energy or heat energy going into the system from the fuel. QC, the amount of energy dumped to that heat sink. Okay? Heat energy supplied to the engine, QH, that comes from my fuel. QC is what gets booted out into the atmosphere during my exhaust stroke. Now, we're then going to talk about the amount of work that an engine does is dependent on the works done per cycle. All right. It also depends on the number of cycles per second, so how fast your engine is working, how far it's rotating, and also the number of cylinders. You might have heard the term of V6. Okay. You might have heard a 3-cylinder type of car. All right, or a V8, and that's referring to the number of cylinders. So in a car, let's just go back, in an engine block, you don't have one single cylinder doing this, you have multiple cylinders that are all working the same. So this diagram is for one single cylinder. So if I have 6 cylinders, I need to multiply that amount of work by 6 because there's 6 times the amount of cylinders. If there's 8 cylinders, I need to account for that as well. All right, important phrase here. This is what we call the indicated power, all right, because it comes from my indicator diagram. I'm working it out using that indicator diagram, the area of that graph, all right. An indicated power is the area of my PV loop, okay, so the area of that PV loop multiplied by the number of cylinders, which makes sense, okay, so this is for one cylinder. If I've got 6 cylinders on the go, I need to multiply it by that number of cylinders. And then finally, how many times it is doing this per second. Okay, because this isn't just happening once, this is happening very, very quickly inside my engine. Be careful here. Okay, they sometimes give you the number of rotations of the drive shaft coming out of your engine. All right, and you've got to remember that a 4-stroke engine, because there's 4 strokes of that piston, it goes up and down twice. Okay, there's only half as many cycles per second. So when we're talking about cycles per second, we are talking about the complete number of cycles. So that's 4 strokes for the piston. Okay, 2 complete up and downs. So if I have a single cylinder, okay, and you're given the rotation of a drive shaft coming out of it, you need to divide that number by 2 to end up with the number of cycles per second. Okay, and when we do some practice questions a little bit later on, I'll highlight that to you. Now we're looking at output power. Okay, so we've been through 3 stages so far. We've looked at input, so coming from the fuel. We've then looked at indicator diagrams, so the work done by the engine. And now we are looking at output power. All right, there's another phrase for this, and get used to seeing this phrase. It makes, or it might make you go, hang on a minute, why have they called it brake power? If we're not braking, okay, it's just raw power. If you think about brake horsepower, okay, it's talking about the power of that engine. So this is output power. How much is coming out that I can physically use to power my vehicle? Now, in order to measure how much I can physically use, I need to know the amount coming out in terms of my engine torque, okay, and in terms of its rotational velocity. So if I'm working out power, I've got T is my engine torque. You can be given that in a question, and omega being my rotational speed. All right. Obviously, the difference between indicated power and my brake power is indicated power is the work the engine is doing. The brake power is the amount that actually gets out that I can physically use. The difference between that is friction. There's going to be friction inside that engine. There's going to be friction between the fuel and air mix and the cylinders. There's going to be friction between the bearings and getting everything done. So we do lose some power overcoming that friction. Now, if I want to work out how much friction I've got, I can work out my friction power. The amount of power that I lose is my indicated power, the work done by the engine, minus my brake power, the amount that I can physically use at the end. Okay, you can also think of this in a different order. So my indicated power, the work done by the engine, is equal to frictional power plus my brake power. Okay, so not all of it is going to be able to be used. Indicated power is work done per second by the engine. That comes from our indicator diagrams. Now, here's where we've got to be really, really kind of key. So you can be asked for any number of different efficiencies, and it all depends on whether I'm interested in indicated power, brake power, input power, etc. So you've got to be really careful about these definitions coming up. First one we're going to look at is thermal efficiency. All right, so what we're doing here, if we're looking at thermal efficiency, we're looking at the work done by the engine compared to the energy that gets supplied to my engine from my fuel. Okay, and if I start looking at thermal efficiency, I've got the work done by the engine divided by the temperature or the heat energy going in. So how much of the heat energy that I put into my engine from my fuel can come out as work. Now, I can do this in terms of heat. So I know that the work done is my energy in, my hot energy, minus my cold energy that goes to my sink. So I've put all of this equation in terms of thermal energy, which is why we call it thermal efficiency. Okay, all of these values are heat energy values. And therefore, that's why we call this the thermal efficiency of my engine. All right. Nice and simple equation for it. So thermal efficiency is my indicated power, okay, because that tells me the work done in my cycle, divided by my input power. So the amount of power I should have from my fuel. And obviously this times 100% gives that as a percentage efficiency. All right. So if I want thermal efficiency, and make sure you're writing this down, it's indicated power divided by input power, which is given by my fuel. Next one, mechanical efficiency. What we're looking at here is how much of the work done by the engine turns into energy that I can actually use to get my car to move along the road or get my objects powered. All right. What's the output energy, my brake power, compared to the work done by my engine? How efficient is my engine? Because this is mechanical, this is turning it into mechanical energy, energy that can do work. All right. We can look at this as mechanical efficiency. And for mechanical efficiency, we need the brake power, all right, the output power, divided by the indicated power, the work that's being done within my engine. Again, we've got to multiply it by 100 over here to turn it into a percentage. So that's mechanical efficiency. How much useful energy is there? Then we can look at overall efficiency. All right. And this is looking at the brake power, so my output power, compared to the input power. Okay, so of all of the energy that I put in from my fuel, how much comes out as usable energy? Okay, fairly simple. We've got overall efficiency as brake power divided by my input power. Shouldn't be a major surprise for you here, but there's also something else worth noting for this equation. All right, and I can look at the different efficiencies I've already looked at. And if I go through this process, again, you're not going to be asked to do this, but I end up with a really interesting equation that says my overall efficiency is actually my mechanical efficiency multiplied by my thermal efficiency. Okay, so if I have my overall efficiency, I've got mechanical efficiency multiplied by my thermal efficiency. And that way, okay, we're looking at how much energy from the fuel gets turned into work, how much energy of that work gets turned into output power, and therefore overall efficiency compares the input to my output power. Okay, really worth noting. So you've got 4 different equations for efficiency there. You need to be very, very clear about what each one is actually asking you. Let's have a quick look at a work example. Okay, and we'll look at this one here. So you've got a vehicle engine with 4 cylinders, uses fuel of a calorific value, 47 megajoules per kilogram, and at a rate of 3.4 times 10 to the minus 3 kilograms per second. Okay, it's operating at 40 cycles per second. Notice that they've given you that nicely in cycles per second, not as a rotational velocity. We've got the PV diagram, all right? So we've got this kind of indicated power. And what we need to do is work out the input power from the engine. Okay, what's going to be important here? Well, I know that my input power is based on fuel. So I've got calorific value of the fuel times my flow rate. Nice and simple, drops out 160 kilowatts. All right, so I'm multiplying. I've got to pick out the useful pieces of information here. Next, I've got to look at indicated power. So if I'm using indicated power, I'm going to have to start using my indicator diagram. All right. Again, okay, let's look at, right, I've got some blocks. I can see that my scale on here is 0.5 times 10 to the 6 pascals. I know that my scale on here is 0.05 times 10 to the minus 3 meters cubed. So I can multiply those together to work out the area of a single block. All right, so we see how that scale, I've got 0.5 times 10 to the 6 and 0.05 times 10 to the minus 3. So I know that every square on here equates to 25 joules. Now, I've got my equation for indicator power. So my indicator loop area times my number of cycles per second times my number of cylinders. Well, I've got 12 blocks. I've got inside my diagram over here, I've got my number of cycles per second is 40 per second, and I've got my 4 cylinders. It gives me a total of 48 kilowatts down here. If I'm then working out my thermal efficiency, I've got indicated power is input power from my fuel consumption, or indicated power over input power, 48 over my 160. I end up with 0.3. Okay, if I turn that into a percentage, obviously it's going to be something slightly different. Okay. I know that's a lot of information about efficiency, so you might want to pause here and have a bit of a break. Okay, we're then now going to look at a diesel engine instead. So there's a slight difference between petrol and diesel engines. You need to know those differences, and you need to know the differences between the diagrams, the PV diagrams for them. So for a diesel engine, we don't actually need a spark plug. We have a glow plug, which doesn't spark. It doesn't create an initial very high temperature. A glow plug is just there to kind of warm that area. What happens, which is slightly different in a diesel engine, is the intake is pure air. So we only get pure air brought into this cylinder, and our piston compresses that air up into a tiny gap. Okay, so into a tiny volume. Now they get it to much, much higher pressures than we had in a petrol engine. Okay, so we compress it to much, much higher pressures and a much, much smaller volume than we do in a petrol engine. And as a result of that, because it's adiabatic, we end up with a very high temperature air within that cylinder. The fuel is then injected, so my diesel is sprayed in to that cylinder at maximum compression. Okay, so it's not mixed, pre-mixed like it is in a petrol engine. I've got pure air that gets compressed, then my diesel gets sprayed in, and because that air is at such a high temperature, the fuel will automatically ignite with contact on the air. Okay, so there's a big, big difference there. We're going to go through this diagram in quite a bit of detail. All right, but then obviously as my fuel ignites, it then expands, pushes my piston down, providing my power stroke. Now, let's have a look at my diagram. So I'm going to start at E. All right, so we're going again from E to A, my induction stroke. Very similar here to a petrol engine. So my piston moves downwards, which increases my volume. It's slightly below atmospheric pressure in order to get it, the air to flow inwards. Okay, so we get our induction stroke, drawing the air in. That's my piston moving downwards to make that happen. Okay. And A to B, so at this point on my PV diagram, is my adiabatic compression. So A to B, we can see volume decreasing, we can see my pressure increasing, and it's compressed adiabatically to about 700 degrees C. That's much, much hotter than we had in a petrol engine. Okay, and obviously, therefore, diesel engines have to be designed slightly differently to petrol engines. That's why diesel cars are slightly heavier. Now, once we have, okay, and once we're at maximum pressure, I get my fuel getting sprayed in to that very high pressure at point B. Okay, and it ignites almost instantaneously, and it forces that piston down rapidly at constant pressure as it expands. So that's why this looks slightly different. On my petrol stroke diagram, I had a vertical line here where I ignite the fuel and the pressure increases rapidly. Here, I already have very high pressure, and as the fuel ignites, instead of increasing the pressure, it forces that piston down as my fuel ignites. Okay, so that's the first part of my power stroke, is a big increase in volume because it's a very high pressure and it stays at pretty much a constant pressure, forcing that piston to start moving downwards. That's why we get a change in volume but no change in pressure. Okay, and as that fuel burns, that's my input heat. That's my energy supply, QH, coming in. Now, after that initial rapid expansion, I then have the rest of my power stroke where the volume increases and my pressure drops. So after that ignition section, okay, it's going to be expanding adiabatically. All right, it's going to be moving down from C to D. You can see the volume increasing, my pressure dropping, just like it was in a petrol engine. Okay, so that part is fairly similar to my petrol engine at that point. Okay, and then D to A, my exhaust valve opens. Okay, and it dumps out a whole load of heat almost immediately. Okay, so this is just the valve opening as a drop from D to A. All right, it's very rapid, very quick. Valve opens. There's a huge amount of pressure drop because there's lots of air or the burnt fuel air mixture that drops down to here. We get a whole load of energy that is exited out into the atmosphere. And the pressure and temperature of that remaining gas fuels because I have let that pressure go. We know that if I expand it or if that temperature drops, we get a drop, a vertical line on here. And then finally, we're looking at our exhaust stroke, that piston coming back up and forcing that air fuel mixture back out. And we're back to the beginning of my diagram. Okay, so we're back to the in stroke, then compression, ignition, power stroke comes out, and then back an exhaust stroke, booting it back out of my cylinder. Really important difference, and they do ask you about this, about the difference between petrol and diesel engines. There's no fuel in the cylinder in this compression in a diesel engine. There is in petrol engines a fuel air mixture. In diesel engines, this is just air. Okay, so it is just air. Because it is just air, that allows us to achieve very, very high compression ratios, okay, without the fuel igniting straight away. So we can achieve very high ignition ratios because it's just air. There isn't heavy fuel in there that interacts and pushes outwards on the cylinder. So I can get much, much higher compression ratios. All right. And the reality is that a higher compression ratio means that my diesel engine is more efficient. Okay, so it's more efficient because that air is at a higher pressure. When I then ignite it and get it out, I get higher efficiency out of my diesel engine than I do my petrol engine. Okay, so that's a fact that you've got to know, that it's the compression ratio, the idea that I can get my air mix to a much higher pressure in a diesel engine than a petrol engine makes it more efficient. One final kind of part on both diesel and petrol engines. So you need to know those big differences between the two. We've been through them fairly extensively. Final bit about this is turbochargers. All right. From turbochargers, you can fit these to both a diesel and a petrol engine. All right. And for both the petrol and diesel systems that we've looked at so far, we're relying on atmospheric pressure pushing air into the cylinder. Now, the idea of a turbocharger is instead of relying on that atmospheric pressure, we create an air pressure that forces more air than would usually be in there into the cylinder before that expansion and compression. Okay, so instead of having just a fixed volume of air at atmospheric pressure, I force air into that cylinder. So there's already pressure before it begins to be compressed. All right. That way, I've got more air at higher pressure in my cylinders and I get a greater combustion. Again, I've got a higher compression ratio that results in a much greater efficiency. Okay, I can convert more energy from the fuel into work within that engine. All right, so just a note on turbochargers, they're not, you need to know what they are and what they do, but you won't really be asked anything more specific on there, but you need to refer it back to that idea of the compression ratio. There's been a lot of information coming your way. It's now time to go over and do the questions on heat engines. In the PowerPoint of thermodynamics questions and answers. Again, there's quite a few. Make sure you are attempting these questions using your notes before looking at the answers. This is entirely, it's not going to help your understanding if you're just looking at those worked answers. What you need to be doing is trying to work out what you need from the notes that you've made so far in order to answer those questions, and then you can kind of check your understanding as you go through. If you get really stuck again, send me an email and then move on once you've done those questions to the next video. Thank you.